In this video, we are exploring the exciting world of memory management. We'll go over the problems with allowing programs to directly access RAM and how virtual memory and paging solve those problems. Here we go. Let's assume we have a computer where every memory access is done using the actual physical address in main memory. Direct memory access creates several problems. The first problem is security. Since there are multiple programs that share the same memory space, all running in parallel, no one really prevents one program from accessing or changing the memory of other programs. It's like the Wild West. Every process could just waltz in and write over another's memory, like outlaws randomly shooting each other in the leg. It's not a question of if things would crash, but when. Fun fact: the first version of Windows, up to Windows 3.11, didn't have any protection against this problem at all. Windows 95, 98, and the Millennium Edition had some enforcement, but still allowed direct access to memory. As you can imagine, this lack of memory protection made them highly vulnerable to crashes and security issues. Any program, whether malicious or just poorly written, could overwrite critical system memory, which led to crashes, data corruption, or even hardware instability. The second issue is fragmentation. Consider a system with a contiguous block of 1 GB of free RAM. The system loads 3 programs. The first needs 200 MB of memory, so the system allocates a 200 MB block at the start. The second program needs 300 MB, so another 300 are allocated after the first program. The third program needs 250 MB, so another block of 250 MB is allocated after the second program. After allocating all memory required for those 3 programs, there's still a free block of 274 MB at the end. At some point, the first program finishes executing and is released from memory. Now, we have a free 200 MB block of memory at the start and a 274 MB block of free memory at the end, which adds up to a grand total of a whopping 474 MB of free space. Next, a fourth program comes along, requests 350 MB of memory, gets rejected, and doesn't start at all. Even though the total amount of memory is larger than what the program requests, it can't get it since the memory is not contiguous. This rigid, fixed mapping of each program to a specific area in main memory causes it to have holes bigger than a traditional Swiss cheese. The third problem is insufficient memory. Older systems didn't have the luxury of having a typical 16 GB RAM we have installed in almost every home computer today. 32-bit systems could only access memory addresses up to 4 GB, so computers could run into the issue of not having enough memory when lots of programs run in parallel. This is relevant for modern computers as well, because modern-day software require much more memory than older programs. So even though memory capacity grew over time, the problem of not having enough memory is still relevant. Aside from security, fragmentation, and insufficient memory problems, directly accessing physical memory also has several smaller issues. Memory is wasted when common code is loaded multiple times. For example, a common C library used by multiple processes must be loaded into memory separately for each process, even though all copies contain the exact same code. This not only wastes memory, but also causes programs to start slower, because each program has to load all common libraries into its own allocated memory space. The final point I'll mention is that direct memory access requires entire programs to be loaded into RAM before execution begins. Since entire programs must fit in memory, large programs might not run when many other programs are loaded into memory. To solve all of these problems, operating systems implement memory access indirection. Instead of locating a memory address based on its physical location in memory, the operating system creates a virtual address space and maps it to physical memory. In a multiprocess system, each process has its own virtual memory space and is unaware of how the operating system maps its virtual memory to physical memory. Since a process cannot directly access physical memory, it cannot modify data belonging to other processes or interfere with their execution. Taking control of physical memory access away from individual processes and giving it to the operating system significantly improves the security and stability of the entire system. I wanted to let you know that I wrote a short ebook that teaches the fundamentals of CPU caches. Looking up this information online can be tedious and frustrating because it's scattered across different sources. On the other hand, buying an expensive book and sifting through hundreds of mostly irrelevant pages isn't ideal either. So I created a short 20-page guide on CPU caches that explains fundamental concepts like cache associativity, architecture, data organization, the read-write process, the locality of reference principle, and the modern cache hierarchy. Every topic includes examples and illustrations to help you easily understand these concepts. Link is in the description below. The second issue that virtual memory solves is the insufficient memory problem. Running multiple applications can quickly consume available memory, especially when using memory-intensive applications. With virtual memory, the operating system can extend the available memory by using disk space. A special file called a swap file or page file serves as an extension of main memory. A program always writes and reads from its virtual memory space, but the actual data could be mapped to either physical RAM or to a hard disk. If enough physical memory is available, a program is loaded and executed normally. But if memory is scarce, the operating system swaps some data to disk, making room for new processes. This mechanism is called swapping, and it allows the system to run applications that exceed their physical RAM capacity at the cost of performance. But mapping every virtual byte to a physical byte would require enormous address translation tables. So instead, virtual memory systems use paging as a way to reduce the size of these translation tables. Paging is a memory management scheme in which virtual memory is divided into fixed-size blocks called pages, while physical memory is divided into blocks of the same size called frames. Most modern operating systems use 4 kilobyte pages and frames, but smaller or larger sizes can also be used. When a program is executed, its pages are loaded into any available frames in physical memory, regardless of whether they are contiguous or not. This approach eliminates the external fragmentation issue, but it also creates a problem called internal fragmentation, where available space at the end of a page is unused because the memory required by the program is not perfectly aligned to the page size. With memory divided into small chunks, it's possible to load only the critical parts of a program before execution, which minimizes the amount of memory used at any given moment. More pages can be loaded as needed during program execution. This is called demand paging. Another advantage of paging is that common libraries no longer need to be loaded separately for each process. All common libraries can be loaded into a set of frames in physical memory and be mapped to by multiple different processes, which allows them to share common pages. Unsurprisingly, these pages are called shared pages. In a system that uses paging, each memory address has two parts, page number and page offset. The page number is... that's the script for the next video.